For the application of work done, we often see the value of force and the type of force involved. Now, for example, if the force applied is a constant force, then the value of work done is given by force into displacement. We have a very simple formula for that, as well as another formula, Fs cos theta, right? But what if the applied force is variable in nature? See, a constant force is very rare. It is not encountered often, but a variable force in actual practice is encountered more commonly, right? So let's learn a way to find out work done by a variable force. For the sake of convenience, right now we are just supposing that the variable force which is acting on a body is in single direction, let's say positive x direction. So here I am making a graph between work done and the displacement, alright. Let's say body, this side I am representing displacement, that is in meters, and here I have the applied force which is variable in nature, this is in newtons. Suppose the body moves, force and displacement are related like this. Force is not constant. A constant force would have been a straight line, right? This is a constant force without any change. But just in case of variable force, the force is could be anything, okay? So in this case we have to find the value of work done for displacement from this point to this point, that is points A and point B. For this, how do we do it? Okay, what is the way, what is our general method to calculate the value of work done? Work done is calculated by force into displacement. Now here, when force is variable in nature, we have shown it in this graph, we can suppose that this variable force is actually made up of very small or infinitesimally small, or let's say just very small displacements. That force is being applied in small displacements, right? Consider one such box. Here from this is a very small distance displacement. Here I have denoted it in x, so let us say this part, very small displacement, is dx, alright. Also, when the displacement is very small, so for very small interval of time, the force is almost constant. That is how variable force is accumulated into the constant force, by taking very small parts, and for every small portion the value of force for this very small portion is a constant, right? If in diagram you can still find that there is a difference in force, that it is variable, all you can do is further distribute its value or smallen the value of dx further diagrammatically, and you will see that the force is constant for a very small displacement, right? So here let's calculate small work done dw for displacement, for very small displacement. Actually small work done is given by force into small displacement x, right? This is absolutely true. Now the small work done is force into dx, which is small displacement. This force is what? It is a constant quantity, which is this force, right? Okay, so how do we calculate the entire force? Okay, before going into entire force, let's do some mathematics on this thing only, F into dx. Here if I name them P, Q, R, S, that means F is this height, which is PR, and dx is this displacement, which is PQ. So ultimately this is length into breadth, which is actually the area of rectangle, area PQRS. That means if I had to find out the work done from R to S or from P to Q, what we did, we multiplied it, considering that force is constant for this small displacement, we multiplied force and displacement, and hence we got this value according to graph, which is PR into PQ, which is actually length and breadth of this small rectangle, and hence it comes out to be the area of this rectangle. So if I have to find out the work done for entire thing, that is from A to B, I have to add up all these individual areas. That is, total work done will be summation of all the individual works done for the all of such small areas. That is, what will I get? After doing this, I'll get area of this rectangle plus this plus this plus this plus this plus this and so on, because right now we have the area of this rectangle, right? Now if we have the area of all the rectangles, so that will actually give me the total area under the curve, that is this whole area, right? So TU, so entire summation of work done is equal to what? This is area under the curve, that is ATUB. Now this is something which can easily be deduced from any graphical relationship between force and displacement. Then if there is a case of variable force and you have to find the work done, just find out the area under the curve and you will get the complete work done, which is the total area under the curve. Now there should be some mathematical expression as well. From this equation we have work done is equal to summation small work done, right? This small work done was the result of force into small distance. So if this distance is very small, that is infinitesimally small, what I can do is I can actually apply a limit on dx tends to 0 summation dw, or instead of dw I can write, what was dw? F dx, right? Summation f dx. So in terms of mathematics, this equation becomes what? This becomes integration. So this is integration f dx, and now I can apply limits as well. This is f dx from P to R, right? So if you have to find the total work done, the displacement should be taken from upper limit to lower limit, or lower limit to upper limit, that is from this part up to this part. So limit f dx, where x is equal to a to x is equal to b, and that is how you find out the value of work done for a variable force.